Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on bending of beams. In fact, we have developed the basic equations of strain and stress by considering the plane of symmetry. We have got the expression of strain as minus mby by EIZZ and sigma x equal to minus mby by IZZ. If you look at the theoretical development, we have recognized it as a plane of symmetry. On the plane of symmetry, we have applied the loading also, and we have got these expressions. We did not stop there. We took a counter example. Suppose I take a beam like this and then have large deformation. When I consider the thickness, what happens to the Poisson ratio effect? So we asked counter questions. When we developed the theory, in order to understand its limitation, we said, because of Poisson ratio, you have anticlastic curvature. Because we are working in small deformation, these equations are applicable. So we satisfied. The moment I go to large deformation, I should work with deformed configuration. We have not attempted to do that mathematics, but we satisfied when I have small deformation, my equations are reasonably good. And we have also got the flexure formula. I am not sure how many of you recognize when I apply constant bending moment, the beam bends. These are like arc of a circle. Why? Because the bending moment is constant along the length. The bending moment is related to the curvature. So you have arc of a circle. Okay. And when we looked at slightly different problem where I have a step, because I said in engineering practice, you need to have a step so that you can locate the bearings. That's a simple modification I have made. But I have not done anything to the loading. The loading is still only pure bending moment. When I have only pure bending moment, I have a very interesting result away from this small zone, which is having this step. I find the fringes are horizontal, and I also have the black line forming at the center. And if you have actually noticed the animation, you would have seen that black line was initially very broad and it was becoming sharper and sharper as we increase the bending moment. Like what we have seen in a beam of constant cross section subjected to pure bending, you see the same features even in a stepped beam. And you also have the definition of neutral axis. In the neutral axis, when I have a triangular variation, the stress value is 0. Fine. You know, photoelasticity plot sigma 1 minus sigma 2. Both sigma 1 and sigma 2 are 0. And you also have this neutral axis. It was a very comforting scenario that whatever we have developed based on simplified appreciation of what is the deformation, we have got the solution and the solution is valid. See, whenever we discuss, we will also have to look at exact solution and compare ourselves, are we getting the right solution, which is done. And what you do that in theory of elasticity. Fine. Even though I am not going to take theory of elasticity in all its completeness, you just look at what happens to this point A, and you know from your bending equation that sigma x is given as minus mzy by IZZ. And I said that you should cultivate the habit of looking at the stress component and putting that as a stress tensor. And what we have developed differential equations defining the equilibrium of the solid. We have not used it in this course till now. And whole of theory of elasticity utilizes these differential equations, solve this problem as a boundary value problem, and you get the solution which is exact, where you don't make assumptions about the deformation. You evaluate the deformation as part of your solution. And if you look at this, in the absence of body force, we have already said in strength of material that shear stresses do not exist because I apply only a pure bending. I have only sigma xx, and sigma xx is found to be a function of only y. So when I differentiate with respect to x, it goes to 0. It satisfies the boundary condition. Is the idea clear? So any problem that you do, you verify your solution with an experiment, whether it is an experiment based on a bending of a beam like this, or when you look at photoelastic fringes. If the experiments are carefully done, what you get in an experiment is truth. And your theoretical development should conform to that. If it is not conforming, then you must find out what is its limitation, what way we can improve. So you should always keep track of that. Experiments are truth if they are performed carefully. If you don't do the experiment carefully, then there is no fun. Okay. Now what I do is ask a question: can beam theory be extended to cantilever beam? I make only one small modification. In the earlier problem, we didn't have shear force. And in this problem, I take a shear force which is constant on the length of the beam. Because it is constant, I find the bending moment varies along the length of the beam. It does not remain constant. It has a linear variation. Whether the solution we have obtained is applicable here is the question. And I have taken a line which is away from the point of loading. I have also taken a line away from the fixed end condition. I have a region here where I can reasonably anticipate my theory should explain the features of the fringe. What is the first observation you look at? What is happening at the center of the beam where you normally think that there will be a neutral axis? It was black in the case of pure bending as well as a stepped beam subjected to pure bending. What do you find here? What is your first observation? Keep these observations. First of all, this is not black. That means you have stresses there. Is the idea clear? Are you able to see? Okay. Now, what I have here is, I have the bending moment varies linearly along the length of the beam. That means when I go from this point to this point, the bending moment is increasing. Suppose I say I can use the flexure formula, which I have it here, and then I put the bending moment corresponding to what I have in the bending moment diagram and evaluate the stresses. The bending moment is varying linearly, and when I move along this direction, you would anticipate stresses also increase. If I have stress occurring here, the same value of stress occur at a lower place because the bending moment is higher. Is the idea clear? That is happening. The bending moment is varying linearly, but I find that this is not varying linearly, but this has a curvature. The observation is correct. But you have one more difference. I have a bending moment varying along the length of the beam. I also have shear stress. I have a new addition because the way the beam is loaded. So I have to account for what way this shear stress is going to influence. The shear force is going to cause you shear stress. And long back we have discussed, you have this as a free surface, this as a free surface. you can find out the distribution of shear stress variation from our strength of materials. Whatever the result I get, because it is a free surface here, free surface here, this should go to 0 at those points. That we have made it clear. Now what I find is, I have raised a question, where is the neutral axis? That is question number 1. Our observation is that I have a color other than black. And we know when I have only the bending stress, I will have the stress state as sigma xx, rest all 0. This is what we have evaluated till now. We have not evaluated what is the shear stress variation. That we will hopefully do it tomorrow. But you can make an observation that the fringe variation, what you observe, is influenced by the shear stress also. Okay. And one can say, when I have this as 0 here, and the center, the color is not black, so I have some value of shear stress. So one conjecture is shear varies from 0 and then goes to 0. Probably it attains a maximum at the center of the beam. One conjecture I am throwing. Okay. Now what you will have to look at is, sigma 1 minus sigma 2 equal to 0 is what my photoelastic fringes gives. In the beam under pure bending, I have a neutral axis where by theory itself, your sigma 1 is 0, sigma 2 is also 0. And I suppose you appreciate, when we label sigma 1, sigma 2, I always label the highest magnitude as sigma 1 algebraically and the lowest one as sigma 2. And in the case of a beam, when I have bent like this, the top fibers are subjected to tension and bottom fibers are subjected to compression. So in the top half of the beam, my sigma 1 will be same as sigma xx. And the bottom of the beam, my sigma 1 will be 0. Fine. Sigma 2 will be your compressive stress. So I will only have positive fringes. And what my observation at the center of the beam shows, I don't have the luxury of saying that both are equal to 0. I don't have that luxury at the center of the beam. Now the question is, can I use this expression for me to find out the bending stress? In fact, that is what we do. We simply take this expression and then look at the bending moment diagram, pick out the bending moment at that point along the length of the beam, use that and calculate the bending stress as if we don't look at what is the influence of shear stress. I get only the bending component by using this expression, and that is an accepted and valid practice. Fine. And you know very well, along the, if I say that this is applicable in the centroidal axis, my bending stress is 0. And we have seen that I have shear stresses transmitted. So I have shear at the center of the beam. Okay. And in the case of an isotropic material, what happens? Normal stress introduces normal strain. Shear stress introduces shear strain. And what we defined as a neutral axis? Neutral axis only elongates, so it does have no elongation and no contraction. Above the neutral axis, depending on the sign of the bending moment, it can contract or elongate. So we are only talking about axial deformation. Even if I have shear present along the horizontal axis, it is not going to influence the strain in isotropic material. I think I also have the isotropic material put. Yeah, isotropic material. Just to remind you that normal stress produces normal strain and shear stress produces shear strain. See, we have been very, very careful in developing the problem. We want to do it only for isotropic materials. Why we do all that? We can understand all this in a simplistic manner and get the core of the problem. The core of the problem is your stress sigma x varies linearly across the beam. Okay, and it reaches 0, and you also know from strength of materials now, when this is bent like this, I have maximum tensile stress here and maximum compressive stress here. So when I put one strain gauge on the top, I put the strain gauge exactly below. I connect them in the Wheatstone bridge in adjacent arms. They subtract. So minus of minus becomes plus. So I have addition of signal. So all that comes from this understanding. So at this stage, what we say is, you can extend it to analysis of cantilever beam. And the moment you say that it transmits shear, I am going to get shear deformation, which will violate plane sections remain plane before and after loading. So I must coin whatever the analysis I do as engineering analysis of beams. Your exact analysis stops at pure bending. Anything other than that, even though we exploit those expressions, you need to carefully look at that as engineering analysis. I was quite happy that you have done a beautiful set of experiments. This is what I said. When you do the experiment carefully, experiment is truth. If you don't do the experiment carefully, experiment is not truth. Fine. And in fact, whoever has obtained this fringe pattern here, I should compliment, because it's very difficult to handle this model in the polariscope and then apply load with your hand. And when you do experiment, you also anticipate results. No one does the experiment blindfolded. Before you do the experiment, you have an hypothesis. You want to see whether my experiment gives that hypothesis. Okay, because I have been repeatedly showing that you get constant color in the case of axial force. That has prompted you to adjust your loading in such a manner that you got constant color. The same experiment done by some other group, you didn't get constant color for the entire length. And you have also done 3-point bending. See, this needs little more attention. We have to see whether my theory, my strength of material solution is giving me the result in all its completeness. We will initiate the discussion. You have to wait for shear force development for you to complete the discussion. And I have this as a 3-point bend, very similar to your cantilever, because when you look at the shear force is constant and your bending moment is varying linearly. So if I can apply my strength of material solution to cantilever beam, I can also apply it to 3-point bending, because this shares the same feature here, okay, on both the sections. And I would like you to take a photograph of this, because these fringe patterns are very, very interesting. That needs to be looked at and discussed. Okay. The moment I have shear force, which I have introduced, it is going to warp the section. So symmetry arguments are strictly not applicable. And I want to emphasize, we don't give up as engineers. We do the analysis. We recognize that we have made an approximation. We label this as engineering analysis. So the bending stress distribution is valid even when m varies along the beam. Now we will have to investigate that this is influenced by the shear stress introduced. And what you will have to look at is, whatever the fringe pattern I have shown here, they agree with theory of elasticity solution. And we have to investigate how do they compare with strength of material solution. If I have to compare it with strength of material solution, I should also know how to calculate shear stress variation across the depth of the beam, which we have not done till now. Fine. We know only the bending stress distribution. And at this stage, I want you to observe how the fringe patterns are. I am also having a bigger blow up of the fringe patterns developed. And what I want you to observe is, the bending moment is varying linearly across the length, it's increasing. And we have seen that fringe is having a curvature. And when you come closer to the load application point, I have this curvature and it has a sharp turn. Is the idea clear? Do you make that observation? And we have to understand whether my strength of material solution, what we are going to develop in terms of shear stress, is good enough to capture these or not. You'll have to wait. But have this observation in mind. When we develop the discussion, we will find out an answer. Okay. And the moment I introduce a shear stress, I am not going to have these sections remain plain. They get deformed. And this is based on the final solution. Okay, you can make certain observation of this. See, this line is perpendicular to this free surface. So when the deformed section is perpendicular, that means the original 90 degrees preserved. What would you say about shear? Shear is 0. Shear is change of the original rectangle. Is the idea clear? And I have also made a conjecture that it is maximum at the center of the beam, and I have the maximum deviation from 90 degrees at the center zone as a deviation. And what I have is the plane sections have warped. Whole of our beam analysis was based on the premise plane sections remain plane before and after loading. On that basis, we calculated the bending stress distribution, bending strain distribution, and that is clearly violated even in the simplest case of cantilever beam. Where does this influence? That's question number 1. And question number 2 is, what is the variation of shear stress? Question number 3 is, what is its magnitude in comparison to bending stresses? All these aspects are important. First answer is, as long as I am having a slender beam, that means the depth is very small compared to its length, shear effects can be ignored. When the depth increases, you have a coupling between shear and axial. There, unless you bring in the shear effects, your beam theory solution is not complete. You also have idealizations for that. Bringing in shear effects, you have what is known as Timoshenko beam. Okay, that's all postponed for your higher level of education. For this course, we will confine to strength of materials, and shear stress variation where the depth of the beam is non-linear. We have always been looking in the case of a twisting of a shaft, shear stress was varying linearly, and in the case of a beam, axial stress was varying linearly, and we find that shear stress variation is non-linear. As we have conjectured based on free surface argument, shear stress is 0 on the top surface as well as the bottom surface and reaches a maximum at the center. That reaches a maximum at the center, I gave evidence from photoelasticity fringes. It was no longer black, I have a color. And we'll also have to graduate when I have a loading that is varying on the beam. And one of the things that you normally take is, particularly when you deal with civil engineering construction, self-weight itself is a load that is acting on the beam. And this you have already developed in your earlier rigid body mechanics. And this is the way you have used how to find out whether you have drawn the bending moment diagram, shear force diagram correctly in comparison to the loading diagram. It's only a recapitulation. Okay, it is not a new derivation. Recapitulation with the symbol on how do we label positive shear stress and positive bending moment. That's the only difference. Otherwise, this you have already done in your earlier course. So I take a small section and then I write all the quantities I know. I recognize that this is having a finite length of delta x. So I anticipate there is a variation of shear along the axis. There is also a variation of bending moment along the axis. and we have taken on a positive surface, positive direction of shear is positive. The only difference is we have learnt it in a different symbolism of sign convention. That is the only difference. Otherwise, you have already been taught how to get this. And I can also say that in a short distance delta x, I can simply put the value as w into delta x, okay, and I can replace this as a force. I can write the force balance and then get me the interrelationship. So if I do Fi equals 0, I get a very important relation in the limit delta x tends to 0, dV by dx equal to W, intensity of loading. Okay. And when I do the same thing for moment equilibrium, I get another very interesting result, dm by dx equal to minus v. If you have used opposite sign convention, you would have got this as dm by dx equal to v. That's where the difference comes. And what it says is, if I know the shear force diagram, I can comment about the slope of the bending moment diagram. So that is one of the ways that you verify your plotting. Hand plotting, you have to do all that. See, if you have a equation, put it in your software and then want to plot, the software will faithfully fit in the curve. But when you do the hand plotting, you have to know how to do it. Okay. And let us solve one very down to earth simple problem. At the same time, it's very interesting. It also has components of modeling. See, consciously, I want to bring in, you become better engineers only when you know how to do modeling. First modeling is, when you have a stack of books, none of the books, if you take 5 books, each of them will have different weight, different size. You don't have one uniform book unless you go and buy a encyclopedic volume, which are published from one same publisher. If you take 10 of them will have the same size, same weight and all that. But if you buy books in fluid mechanics, solid mechanics, material science, all of them will be different. So the first idealization you have to make is translate this into a uniform loading. You should not exceed that. That's what I want you to recognize. Okay. And what is given is, you can make a nice, elegant support by having a simple glass plate. This is of length 900 millimeter and depth 200 millimeter. It can accommodate many of your books. And it also says, determine the average weight of the books per unit length which can be placed on the shelf if the supports are in the optimal position. You have to understand what is an optimal position. In fact, there is embedded clue in your question itself. The supports are not put at the end. The support are put in a manner that this, whatever the length A is greater than L by 2. You are given a clue. And as engineers, we have to find out where do you put the supports. See, if you are not done engineering, you would normally put the support at the ends. You think that is stronger. That's what you would do. What we call as common sense, we jump to such conclusions based on prior training. And I have also asked you to do this as your tutorial to get the shear force and bending moment diagram. Okay, so that I can go and handle those portions little faster. Okay. First thing is, you have to get the reactions, and that is you do by sigma Fi equals 0 and Ma equals 0. It's very straightforward. So I get the reactions as WL by 2 at both the supports. I've also been saying that when you have a problem like this, you should be able to draw the bending moment and shear force diagram quickly. Fine. So if you give me this, I will find out, for drawing my shear force, I will find out what is the shear force at this point. I will find out the shear force at this point. That is good enough for me to draw the complete shear force diagram. Okay. And if I have to do the bending moment, I'll also find out what is happening at the center. So 2 points are sufficient for me to draw, 3 points are sufficient for me to draw the bending moment. Because I have the loading is W Newton per meter, I anticipate my shear force for the entire length of the beam to be the first degree curve, because I know dV by dx equal to minus W. I use that. And when I go to bending moment, I have dm by dx equal to minus V. So if the shear force is a linear curve, bending moment will be a parabolic curve. So all that information you use it. And if you do from the conventional point of view, I can find out what is the expression for m. If I take a section and then do it, I can do this. So I will do that for one section, another section, and the third section. That is for for completeness. Completeness, you have these expressions. I can get it for this. But when I want to plot, when I start here the shear force is 0 as well as bending moment is 0. So I know 2 points already to start with. So if I know this, at this support I have WL by 2. Actually, from this point, I will go up by WL by 2. That's what your mathematics also will give. I'll go up by WL by 2. And if I know this point, I know this is a straight line, I'll join these two. Again, go up by W by 2, WL by 2, and then come back to 0. So you can draw this very quickly. You have to build up that acumen. As you learn the course, you can't be saying that you will take half an hour to solve this problem. Okay. And similarly, when I go for the bending moment, I know that this is a second degree curve. The question is whether I should draw it like this or draw it like this. That you look at based on your slope. See, slope is 0 here, slope is positive here. You have dm by dx equal to minus V. When V is 0, slope is also 0. When V is more and more negative, slope is also more and more positive. So that is how you decide why I have to plot the curve like this. And now you can quickly say, as an engineer, suppose I put the support at the end, what would be my bending moment diagram? Bending moment diagram will be a parabola from this end to this, and your bending moment peak value will be much higher than this. Do you see that difference? So one clue you get is, by adjusting the support, you can achieve a situation where you can minimize the level of bending moment maximum occurring in the plate. So that is a design tool. See, you don't worry about whether it is a positive bending moment or a negative bending moment. Because whether it is a positive bending moment or negative bending moment, you are definitely going to have same maximum stress and maximum compressive stress. Instead of occurring at the top fiber, it may occur at the bottom fiber. That's the only difference. So even the sign of the bending moment doesn't matter as long as my cross section remains same and symmetrical. Suppose I have a cross section where the distance also matters. Okay, there you may have to find out whether the compressive stress is more or tensile stress is more if I have a brittle material. If I don't have a brittle material, I don't have a problem. For ductile material, your tensile strength and compressive strength are identical. For a brittle material, it's opposite. You have tensile strength is hardly anything and compressive strength is 10 to 12 times. So there it matters. But glass plate you have taken, it's of a constant cross section. And with this itself, you can find out, by equating these two, you can find out the optimal position. In order to aid your thinking better, I am also plotting this when I have A is greater than L by 2 and when I have A is less than L by 2. Greater than L by 2 is what we have got earlier also. When you substitute the numbers are easy to recognize and then see how they vary. And when I have A is less than L by 2, I have everything on the one side. So if I start from this, I will not be able to find out the optimal position at all. So only if I start from this kind of a bending moment diagram, I have an opportunity to find out the positive bending moment and negative bending moment and equate the two. So it's a design scenario. So what we do is we simply equate the two, equate the magnitudes, okay? Equate the magnitudes. The same shear force and bending moment diagram is replotted. I equate these two values. I get a quadratic expression of A squared minus 4AL plus 2L squared equals 0. From this, I can solve for what is the value of A. So that means I have adjusted my supports in such a manner, whatever the bending moment I get here, I ensure that this peak and this peak are of the same magnitude. So that's the best optimization that you can do. For the given problem, that's the best optimization I can do. So I get, when I substitute this being a quadratic expression, I'll get two roots. You have to select the root which is appropriate. Only this is will lie within the beam. Okay. So I have this as 527.21 millimeter. And once you substitute here, once you apply the beam theory, hopefully the beam theory is applicable. We have to verify. We have to verify with theory of elasticity. We have not done that verification. We will also do the verification, and if the deviation is small, keep our eyes half closed, pat our back, I have got the value which is good enough for my design. This is how engineers operate. Okay, you have to get the core of the problem. That is more important. The core of the problem here is bending stress varies linearly over the depth of the beam. When I apply an axial load, it is constant. To recognize that varies linearly was the biggest challenge the scientific community faced. It took 400 years. You should recognize that. We will also revisit the history today. Because you are now more equipped with what is beam theory, you can go back and appreciate what aspects they could reveal, what aspects they could not find out in their development. Okay. So I have this bending moment is equated, and you have got this expression. So when I substitute and then substitute the value of A which I calculated, I get the maximum bending moment magnitude is like this. And I have the bending equation is available. So whenever you solve a problem in bending, please write this in one corner and start, because you are going to exploit this equation. So I can write sigma bending max as sigma MB max divided by IZZ into I max. And then you have the cross section like this. I have this as the breadth and height. So I have for this rectangular cross section how to calculate the moment of inertia. And when I use the information given in the problem that it cannot exceed 10 MPa, I find out what is the value of W. I have this as 0.48 Newton per millimeter. Let me ask you a few more questions. I am not going to give you answer. Fine, I want you to think. Suppose I want my W to be not 0.48, I want this to be doubled. What are the options that I have for me to do? It's obviously going to exceed the 10 MPa limit. That means I have to strengthen the beam in some form, isn't it? One possibility is you take another glass plate, put it. That is one possibility. The other possibility is, instead of a 5 millimeter glass plate, find out what is the thickness of the glass plate you have to go. That is option number 2. What is option number 3? Simply increase one more support. You get the point? See, I should also provoke you to find out, when you go to a design scenario, there is no one solution for a design. You will have multiple solutions. Depending on the context, one of them may be really applicable. So I want you to exercise this. So you find out what is, when I want to double it, what should be the thickness I should have with the same support, because that's the optimal support. Suppose I have 3 supports. You have to wait until you develop a deflection because it's a continuous beam. you need to find out the forces. Only then you can solve the problem. So keep that at the back of your mind. So it's a very interesting problem. Okay. Now let us look at whether this is supported completely by theory of elasticity. There are surprises. Okay. You have not calculated the shear stress. Okay. And you can take it that this is varying parabolically. I said non-linear. Anything other than linear, we'll say non-linear. It may be even be a simple second degree curve. Okay. And we have obtained from strength of material that bending stress varies linearly. Please make a sketch. This you will not find it in any books that you have access to. And also appreciate stress magnitudes are not to scale. That's also very important. We are only discussing the variation over the depth of the beam. And you will find that what we get from strength of material up to this point, it is perfectly correct. We have also done discussion on free surface. Suppose I want to do the discussion on what happens this surface. Is this surface free? I am deliberately applying a vertical load. How can that be free? In the development of bending of a beam with constant bending moment, we have idealized sigma y as 0. Isn't it? Sigma y as 0. But this is one of the most common loading that you have, and you are definitely applying sigma y. You are applying a force to generate sigma y. So when I go and solve the problem as boundary value problem, taking the differential equations, I am definitely going to have sigma y, and it will die down to 0 at the other edge. And there is also another surprise. Even the linear variation of bending stress is no longer supported by theory of elasticity. You have a correction term to sigma x. So you have two additional quantities. Sigma y exists, and I have not drawn these to scale. You will find that these are second order effects. The small variation can be ignored when you use the expression for bending stress which were developed in strength of materials. Is the idea clear? So you have to understand that we are doing only engineering analysis. So you have to appreciate the limitation. And I have raised a point in a 3-point bending. There is something we have to discuss about the shear stress, whether strength of material predicts it correctly or not. You have to wait until we develop what we do that in strength of materials. Okay, then compare it with theory of elasticity. So you should appreciate that whatever the expression that we have got in strength of material is very useful, but it has its own limitations. Appreciate the limitations. And let us go back and quickly go through the history, because we have already seen this. You can appreciate certain aspects now better. See, Leonardo da Vinci was the first one. He established all the essential features of the strain distribution while pondering the deformation of springs. That is his wisdom, we have to say. And for the specific case of rectangular cross-section, Da Vinci argued equal tensile and compressive strains at the outer fibers. That's what we also say now in strength of materials. He could also say that the existence of a neutral surface and a linear strain distribution. What he could not achieve, he did not have Hooke's law, so he could not translate this understanding to stresses. Okay. And second one is, he had to wait for the mathematical formulation of Bernoulli and Euler. And he was also not in a position to give recommendation how to design a beam. How to, if I know the strength of the material, how to get the dimensions of the beam. And when you dig the history, you find that he has written a book that he has all this information. But this was found out only in 1967. So all the early researchers, without his book, they had to struggle and find out what is the beam theory. So Galileo was the first person. He said the beam strength was addressed. and he was able to give some numbers based on his experiment. Even at that time, I said this was a very difficult experiment. Okay. Can you recognize he's made a statement, rulers offers more resistance when lying on the edge than when lying flat. Do you agree with this observation or not? Do you agree with this observation or differ? I don't get the answer. You nod your head. What do I make out of it? Do you agree or not? You agree. Can you tell me how you say that this is better than this? What is the aspect that you can say mathematically? Very good, very good. I'm happy. So bending rigidity, and I have EIZZ, and you know very well IZZ for this cross section is very high compared to this. So this observation was correct. They were learning it experiential knowledge was very good. Okay. I have been using this beam. This is also made of plastic. This has some cross section, and this has cross section which is much larger. And you know very well that this has hardly any bending rigidity. And I needed this for me to show your warping in case of twisting, and also for anti-clastic curvature. Okay. So what made the difference between the two? This has more rigidity than this because of its Young's modulus. Okay. So EIZZ is a very important aspect when you are looking at anything to do with bending. Similarly, GIP for torsion. And he had a good idea of how the beam failed and things like that. Okay. And he could not find out the variation of stress. The variation of stress was very difficult. He had some idea that this failed here. It said it's because they were accustomed to only axial force transmitted. So the same idea of equal force was obscuring their thinking. And now you can say that he had taken a complex problem. Okay, because I explained how your cantilever beam is difficult to handle because it has shear force, and shear force introduces plane sections do not remain plane, and you have bending moment varying. We were very clever. We took a problem deliberately that it will transmit only constant bending moment. He didn't have that luxury. So he didn't have that luxury. That is why he faltered. He could not proceed beyond a particular point. And you also see that this beam is not slender. Okay. The problem is complex because it is not a slender beam. The depth is important. I said the shear and the axial force, the coupling takes place when these two are the depth is comparable to the length. And material, he was not having isotropic material. He was having wood. So they could not proceed. So when you want to solve a problem also, you should know how to simplify and get the core of it. And Mariotti had some idea that there is a variation is linear. He was also not able to succeed, but he showed both variation like this as well as variation like this. But it's not clear why he obtained two of them. So they were very close to the solution but not achieved it. He could also say the neutral plane. And Parent, he got this as triangular, and he had this neutral axis shifted, and stress distribution from tensile at the top, phase to compression at the bottom. See, they were always looking at bending like this, okay, like what I was showing. So the top surface is in tensile and bottom surface is in compression. So he was able to do. And so the triangular variation is credited to Antoine Parent. The breakthrough came only with Euler and Bernoulli. They linked load and curvature. Unless they could bring in the deformation, the beam problem was not solved. Okay, so that took such a long time to develop. So he was a Swiss mathematician, another is a Dutch mathematician. They independently derived beam bending formulae and are credited with development of beam theory in 1750. But the actual distribution was credited to Coulomb. And if you look at the distribution, the contribution by various scientists, we summarize. Da Vinci had all the idea, but his book got lost. Galileo could design beams, could solve problem halfway, but he assumed that the stress is uniformly distributed. And you have first appearance that it is varying in a triangular fashion in one form. He also had mentioned this, okay, without assigning reasons. And Parent correctly said that you only have this kind of variation. His neutral axis is shifted. And finally, you have Coulomb, who has solved the problem of beam bending. So what you have learned in the few lectures has taken 400 years for its evolution. It's not something simple. So if you have doubts, don't feel annoyed. Great minds have these doubts, okay, and they didn't have access to simplified experimentation. And in fact, even in IIT, see this I could get easily in a commercial shop. And in order to show your warping and torque, I had to get a material which is very soft. We had to take some effort to get this material done. Okay. So in this class, we have looked at what are the limitations of strength of materials approach to beam theory. We said it is derived only for a beam of constant bending moment transmitting. Anything other than that, it can be considered only as a good approximation of engineering analysis. Thank you.